Alrighty, happy Monday, everyone. This is 3.1 Graphing Polynomial Functions. Oh, excuse me. Our goal is to identify features of polynomial functions. A function is something that passes the vertical line test where there's one y value for each x. Polynomials are just expressions consisting of variables and coefficients. So let's just start this off. Example 1, classifying polynomials. Write a polynomial in standard form, which means from highest to lowest degree, or exponent, to identify the lead coefficient, which for you to define the lead coefficient, it has to be in standard form, the degree, which is the highest exponent, and the number of terms. Now, I pre-wrote these notes just for ease of narrating them. Feel free to pause the video at any time to write this down. I don't want you to feel rushed with this. So this is a polynomial. To be specific, this is a trinomial because there are 3 terms. Now, a couple things. I'm sure you're easily able to identify the highest degree. We see x to the third, that's the highest. The lead coefficient, however, is not -4. That's why this has to be in standard form. You go from highest degree to lowest degree. So x to the third, x squared, and technically that 9 is x to the 0, but we don't really worry about that part. So after you put your polynomial in standard form, you go through and identify your lead coefficient, in this case is 2, your degree is 3, and this has 3 terms. That one you're always able to tell just by looking at it, but always put it in standard form first. So go ahead and pause the video. These are your try it questions. And when you unpause it, I'll start filling in my answers. Okay. Let's start by putting this in order from highest degree to lowest. So x to the 4th is the highest, followed by x to the third. We have no x squared, so we move on to regular x. Lastly, our coefficient. Our lead coefficient is -3, clear as day. Our degree is 4, and number of terms, there are also 4. Letter B, again, organized from highest to lowest. Looks like x to the 6th is our highest, followed by our x to the 5th. And then we have x to the 4th, 4x to the 3rd, no x squareds, but we have a regular x. Lead coefficient is 2, our degree is 6, and number of terms, 1, 2, 3, 4, 5. That's all there is to that. Okay. End behavior of polynomial functions. This is where we get into some nitty-gritty stuff with our graphs. So example 2, end behavior of polynomial functions. The end behavior of a graph describes what happens to the function as x approaches, positive and negative infinity. The right and left sides of the, I don't want to say grid, let's say coordinate plane. So we're analyzing the domain and range. So for each of these things here, I'm going to show you what these graphs look like. So this is an odd degree with a positive lead coefficient. So by an odd degree, if I go back to our triads from before, these were both even degrees. Their highest degree was even. This is what your graph will look like when your function has an odd degree. For example, f of x equals x, that's our standard x graph. We know it goes up when we read the graph from left to right. Always read a graph from left to right. So as x approaches infinity, y approaches infinity. What I mean by that is, as we go to the right on the x-axis, what happens to the function? Well, it goes up towards infinity in the y direction. And on the flip side, as we go to the left, as x approaches negative infinity, what does the function do? Well, it goes down towards negative infinity. That is what your standard odd-degreed function will do. It might look a little different each time, like you see this blue one looks kind of funky, but it still follows the same end behavior. As we increase in x values, the function is increasing in y values. And as we decrease in x values and go to the left, so does the y. Okay, make sure you take time to write these. I know it can be a lot to draw these graphs, but these examples are really fantastic. I pulled them from your textbook, and I think they'd be fantastic to have in your notes. All right, next part, odd degree function, but the lead coefficient is negative. And you guessed it, negative coefficients just flip the graphs. So instead of our functions going up, they're going down. So the way we describe the end behavior, this stuff right here, flips as well. So for my red graph, as we increase in x values towards infinity, the graph is now going down towards negative infinity. As we decrease in x values and look to the left, the graph goes up. That will always happen for your odd functions with a negative lead coefficient. The cornerstone of odd functions is that your answers will alternate for your for your y's. They go in opposite directions like this. You see there, one's reaching up, one's reaching down. When we get to even functions, which is the next part, take a look at this. Even degree functions with a positive lead coefficient. The most simple even degree function is our x squared. It's a parabola. And then we have one that looks a little different. You know, it's got an x to the fourth and a bunch of decimals, but the end behavior still resembles a parabola. If I were to cut off this part of the graph and you just looked at the arrows, you'd see, hey, cool, they're both reaching in the same direction. That's how your even functions work. And it's because no matter if you plug in a negative number or a positive number, your answer will come out positive. So negative 2, 4, and 2, 4. That happens for any even degree. Even if we plugged to the fourth power in here. So let's see, 2, 4, 8, 16. Same thing, comes out positive. That's why in our end behavior description, they both go in the same direction. As we increase in x values, we increase in y values. As we decrease in x values, we still increase in y values. That's going to happen for any even function, unless we have a negative lead coefficient in which they flip. So now instead of going up, they're both going to go down. So when you describe the end behavior of a polynomial, this is what you're doing right here. You're saying, as we approach the extremes of the graph, as we go to the left and to the right, is the graph going up or going down? And one last thing, when I say graph, this is something important I discovered last year, I don't mean this entire thing. That entire thing is a coordinate plane. The graph are the colored parts that I put on there. A graph is a picture of a function. So don't get confused on that part. All right, that's it for day one. Oh, no, I'm so sorry. It's not. These are the triads. So give the end behavior of each function's graph. So go ahead and pause it here. All right. So all of this mumbo jumbo here actually does not matter. What we are concerned with when we're looking at end behavior is the highest degree. I see an even function and the lead coefficient is positive. So I know in some way, shape, or form, this thing may look really weird, but the end behavior is still going to be both approaching infinity. They're going to be going up. And yes, these functions sometimes look this weird. All of those different terms give the function different dips and dives and minimums and maximums. Letter B, I see an odd function with a negative lead coefficient. So my best advice for remembering how your odd functions work is picture a regular odd function. As we go right, it goes up. As we go left, it goes down. It should match what you have. However, This one is negative. So we're going to be having the opposite. This one's going to be decreasing. Stonks are decreasing. As we go to the right, it goes down, and as we go to the left, it goes up. So as x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. All right, and that is the end of your day 1. Your homework is at the end of your notes. Take your time with this. And remember, if you're ever confused, just ask me questions.